Hello, today we are looking at section 3.4, which is about concavity and the second derivative test. So you can see our learning objectives up at the top. We are going to determine the intervals on which the function is concave up or concave down. We will find any points of inflection of the graph of a function, and we will talk about how you can apply the second derivative test to find the relative extrema. Remember, you can also use the first derivative test. So this is another method, which is sometimes faster, but sometimes not necessary. Okay, so first off, I do highly recommend that you watch this Khan Academy video before starting. So that's linked. It gives a very good overview of the concept that we'll be talking about today, concavity, and it has some good visuals as well. So I do recommend you watch that first. And if you already have watched it, then let's get started. So the definition of concavity is this. Let f be differentiable on an open interval I. The graph of f is going to be concave up on that interval, so concave up on I, the interval I, when f prime, so the first derivative, is increasing on the interval, and it will be concave down on the interval if the first derivative is decreasing on that interval. So let's talk about what this means. So first of all, concave up looks like a smiley face. Concave down is like a frowny face. And many functions have, in different intervals, it will be one or the other. So it'll switch from concave up to concave down. Now, in these two images we have below, they're strictly concave up and concave down. So let's talk about what I mean by f prime is increasing or f prime is decreasing. So remember that f prime, the derivative of f, is representing the slope of the tangent line. And so visually, what's going on here is, here we can see, we're going to start with this first image. If I drew in a tangent line right here, that tangent line right there has a negative slope. And as we continue moving across the interval, we can see this first one that I drew is more steep. So it's more negative, becomes less negative, then it becomes 0 down here at the bottom, becomes positive, and then it becomes more positive. And so what's going on is that the slope is increasing. The slope of the tangent line is increasing from left to right. Let's just abbreviate. Increasing. That's a weird abbreviation. So it started off negative, and then it got less negative, it turned to 0, and then it became positive. So this is an example of concave up. If you think you're going to have trouble remembering what up and down are, that's one little fancy way to remember it. Notice that in this image, the graph of the function is always above the tangent line. So if when it's concave up, if you draw in the tangent lines, you can see that your graph is lying above those lines. So graph is above tangent lines. And like I said, f prime, so the slope of the tangent line, which is the derivative is the slope of the tangent line, f prime is increasing. Okay, so now let's observe a concave down function. So here we can see we start out with a positive tangent line slope, then it becomes a little less steep, a little less positive, turns to 0, and then it goes into the negatives, less negative, more negative down here. So here the slope of the tangent line is decreasing. So this one is called concave down. Here's your little fancy way to remember it. So for the up, you have the u, and for the down, you have the n. The graph lies below the tangent line. So on the previous one, the graph was always above the tangent line, and here we can see our graph always lies below the tangent line. And finally, f prime is decreasing. The slope of the tangent line is decreasing. So those are just some different ways to think about concavity and to kind of like holistically understand what is going on here. So of course, in calculus, there is a test for concavity. Let f be a function whose second derivative exists on an open interval I. If f double prime of x, so the second derivative, so we're looking here right now. So if your second derivative is greater than 0 for all x in that interval, then the graph would be concave up. If your second derivative is negative for all x in the interval, then the graph of f is concave down. So we're just going to, and if, this should be double prime. Sorry, this should be double prime. If f double prime of x equals 0, then it's constant. So let's move on. These should also be I. Sorry about that. Okay, so we're going to look at this example down here. So use the graph of g of x to answer the following. So we're just going to find an interval where g prime of x is less than 0 and g double prime of x is greater than 0. So let's think about what this means. So hopefully you remember from last class that we talked about when the first derivative is less than 0, that means that your original function is decreasing. So when I see this, that tells me g of x, the original function, is decreasing. And then when I see the second derivative, I'm thinking about concavity. So for the first derivative, if it's positive, it's increasing. If it's negative, it's decreasing. For the second derivative, if that's positive, then the original function is concave up. And if that second derivative is negative, then the original function is concave down. Oops, concave up. Okay, so we just want to identify a portion of this graph where it is decreasing and it is concave up. Okay, so I see a few regions where it's decreasing. I'll highlight in orange. Decreasing here, and it's decreasing here. And so out of those two places, I'm just going to try to find an interval where it's concave up, so where it looks like a happy face. And so I see there's a few different places you could choose, but right here would be a nice, easy one. So from -2 to -1. This is just one place where I'm noticing that the function is decreasing and it's concave up. Now for part B, we want to find just one interval, any interval where still we are decreasing. So g of x is decreasing. But now we want to have our g of x be concave down. So we want to be decreasing and concave down. And so again, there are a few different places we could choose, but I'm going to pick this one here. So here we are concave down from 1 to 2, +1 to +2. Okay, so for this next portion, we are going to try to visualize what's going on in each of these scenarios. So the second derivative tells the change in the rate of change, right? So the first derivative is the rate of change of your function, and the second derivative is basically the change in that rate of change. So like I said, what you really need to know is that the first derivative tells you if your function is increasing or decreasing, and the second tells you if you're concave up or concave down. So let's look at this first situation. This top one tells me f is increasing because the first derivative is greater than 0. The second derivative is greater than 0. That tells me f is concave up. And so we're going to try to sketch this. So we want our function to be increasing and concave up. So we want it to be going up from left to right and looking like a smiley. So this is kind of what that would look like. And what's going on here is that we're increasing slowly at first and then faster. So f is increasing at an increasing rate. Okay, let's look at the next one. So for the next one, we have f is increasing still because the first derivative is positive. But now for the second derivative, we're negative. So this tells us that f is concave down. So if we sketch this, we still want to be increasing, going up from left to right, but we're going to start off increasing fast and then slow down. So something like that. So this is f is increasing at a decreasing rate. So it starts off fast, then slows down. Okay, so for the rest of them, I'm not going to write down. We're just going to think about it. So for this next one, let me number them. For number 3, we have f prime is less than 0. So now f is decreasing, but it is concave up. So it's decreasing, but concave up. So it has to look kind of like the left side of a happy face. Decreasing, but concave up. So we start decreasing fast and then we slow down. So f is decreasing at a decreasing rate versus the last one. Let's see. So f prime of x. So we're still decreasing, but now, so this is for number 4, the function f is decreasing, but the function is concave down, and so that would look like this. So f is decreasing at an increasing rate. It starts off decreasing real slow and then drops off, starts decreasing really fast. Okay, so this now brings us to points of inflection. Points of inflection, also known as an inflection point. So an inflection point is just where your graph changes concavity. So last time we talked about how relative maximums and minimums were where you kind of like switch from increasing to decreasing. But now points of inflection are where you switch concavity. So if the graph of f changes concavity, at that point, so at a point C in your interval, then the point is a point of inflection. And there's a theorem that says if a point is a point of inflection, then either, I'll highlight this, then either your second derivative will equal 0 or your second derivative will not exist at that point. Okay, so graphically, let's look at points of inflection. So this is the graph of g, and g is a twice differentiable function, which means you can take the derivative twice. Which of the labeled points are points of inflection? So it will be a point of inflection if it switches concavity. So let's first think about this. I'm going to do some highlighting. So I'm going to highlight this first region all the way to the point A. And in that region, that is concave down. And a few different ways you can think about that. Right? You can imagine drawing the tangent lines. It's below the tangent line. You can kind of see it looks like a sad face. So however you need to think about it, you can look back up at the top. I wrote those different ways. Now, what about from A to B? Oops, I wanted to highlight. Okay, so from A to B, so this region here, this now is concave up. This is concave up. So would A be a point of inflection? Yes, it is, because we switched from concave down to concave up. Okay, let's look at our next region here. The next region is from B to C. Okay, looks like I am concave down here. I am concave down. And then finally, I have this last region. And I can see right away when I stop at D that that's a minimum point. That is not a point of inflection. So a local minimum is not a point of inflection. This last region is concave up. So the points of inflection here are A, B, and C. So at A, B, and C, the graph changes concavity. Switches concavity is another way to say it. Concavity. Therefore, these points are points of inflection. Okay, so let's practice a little bit more. So that we started off thinking about all of this graphically, so thinking about concavity graphically, points of inflection graphically, and now we're going to talk about how to think about these algebraically. So we are going to determine the points of inflection and discuss the concavity of the graph of this given function f of x cubed minus 3x plus 2. So definitely when you're dealing with points of inflection and concavity, you want to work with the second derivative. If that's all you're asked about, you are only going to work with the second derivative. In order to find the second derivative, you need to find the first derivative. So we're going to do f prime of x. Luckily, this is a polynomial, 3x squared minus 3. Nice and easy. And now I'm going to find the second derivative, and I'm just going to end up with 6x. And so points of inflection are going to possibly occur, not definitely, but possibly occur when your second derivative equals 0 or where it does not exist. And this is 6x, so there's nowhere that this won't exist. It exists for all real numbers, so we don't need to worry about that. But we will set it equal to 0, and we will get x equals 0. And so right now, this is a possible point of inflection. Not definitely, right? So to actually check it, we are going to use a sign pattern chart because we know a few things now. We know that if the second derivative is negative, our function is concave down, and if the second derivative is positive, it is concave up. We also know that a point of inflection occurs when our graph changes concavity. So what we should do is make a sign pattern chart, put our possible point of inflection on there, and then evaluate the second derivative on either side. So we've already done this with the first derivative, now we're doing it with the second derivative. So to the left of 0, will f double prime of x be positive or negative? Well, if you plug in, so you're going to plug into this function here, -1, for example, you'll get -6. So f double prime of x will be less than 0 over here. Versus over here, f double prime of x is going to be greater than 0. If you plug in a number like 1, you get +6. If you plug in 2, you get +12. It's positive. So what does this tell us? If f double prime of x is less than 0, that information tells us that f is concave down. And if f double prime of x is positive, that tells us that f is concave up. And so, can we see a point of inflection? Yes, the graph switched concavity at 0, and therefore 0 is a point of inflection. So let's write this out all like using really good explanations. So 0 is a point of inflection since f double prime switches from negative to positive. And we were also asked to discuss the concavity. So let's say f is concave down. Excuse my spelling. Too many C's and N's. Concave down on the interval negative infinity to 0. And f is concave up on the interval 0 to infinity. And on something like the AP exam, you would want to say, like, explain how you know that. Like, f is concave down. Let's just write it to practice. Since f double prime of x is less than 0, and since f double prime of x is greater than 0. So on the AP exam, the sign pattern chart is not enough. You need to provide an explanation and how you know that that part is true. Okay, moving on. So we're almost done here. We're going to talk about the second derivative test, and then we're going to do one example that's a bit more complicated of like putting all of these concepts together. So this is the second derivative test, and we'll talk more in class about like when you would use the first versus the second. But the second derivative test says let f be a function such that f prime of c equals 0. So the first derivative equals 0, and the second derivative exists. Okay, so the first derivative equals 0, and the second exists. If f double prime of c, so the same point, is greater than 0, then f has a relative minimum at c. And if f double prime of c is less than 0, then f has a relative maximum. And so visually you can see, remember that when f double prime of c, so the second derivative, is less than 0, that means that you are concave down. And so there we have a maximum, right? If we're concave down, we're going to have maximum, and that would be when the first derivative is equal to 0. So that's what's going on here. And then similarly, if we're concave up, so f double prime of c is positive, and if f prime of c is the first derivative of c equals 0, then I know that we have a minimum. So let's practice this. Oh, and this is also important. So if the second derivative ends up equaling 0, then this test fails, and so you would need to use the first derivative test. Okay, and the reason you would use the second instead of the first is sometimes it's faster. It's just kind of situational. So we'll do it this way. We'll use the second derivative test, and then I'd encourage you to go ahead and also find the relative extrema using the first derivative test on this same problem to see which method you prefer, because you can use either. Okay, so here we go. We're going to first find f prime of c. And then this is what we need. We need f prime of c to equal 0. So we're going to set this guy equal to 0 and solve. Factor out of 3. Factor it a little more. that right? X, oh no, minus 1, x minus 1. Okay, and we get x equals 1 or 5. Those would also be the critical numbers of this function. Okay, and so what we need to do now is we need to take each of these values and we need to plug them in to the second derivative, which means we first need to find the second derivative. It would be 6x minus 18. And so for the first derivative, what you would have to do is you'd have to make the sign pattern chart, put the 1 and the 5 on there, test the intervals. For this one, you find the second derivative, and then you plug in each of these values we found into that function, into the second derivative. So we're going to do f double prime of 1, and we are going to do f double prime of 5. And so we're just substituting these numbers into the second derivative. And here we're getting negative 12, and here we are getting positive 12, right? 6.1. Yeah, okay. So what does this mean? So since since f prime of 1 equals 0, because that was the first criteria, we need that thing to equal 0, and f double prime of 1 is less than 0, a local max exists at x equals 1. Because this is telling us that at 1 we are concave down, and also at 1 there's a horizontal tangent. So if there's a horizontal tangent and you're concave down, that is a maximum, a local maximum. And then similarly here, since f prime of 5 equals 0 and f double prime of 5 is greater than 0, so here we're concave up, and we have a horizontal tangent happening at that value 5. This is a local min. Exists at x equals 5. Right now I'm not spending the time to, you could plug the 1 back into f of x to get the full ordered pair. You could also do that with the 5, but for now I'm just saying where the max and min exist rather than what their actual points are. Okay, so here's our last problem, and this one is a tad complicated, so bear with me. We are going to kind of put all of these concepts together that we've learned in chapter 3. So we're going to find where f, this function f, is increasing or decreasing, where it's concave up, concave down, and we'll find any points of inflection. We'll also find the local extrema, since, I don't know, it kind of appears anyway, so I didn't write it down, but we'll find that as well. So where it's increasing and decreasing, that's using the first derivative. And then all of this other stuff is using the second derivative. So that whole second part is what we've talked about today. So let's start off by differentiating this function. Don't write too big. Okay, so we're going to bring the 5/3. We're going to have x to the 2/3 plus multiply that 2/3 by the 5/3, that would be 10/3, x to the negative 1/3. And then you can rewrite this just a little bit nicer. So this would be 5x to the 2/3 over 3 plus, because my goal here is to make a common denominator, 3x, over 3x to the 1/3. And so to make a common denominator, I would need to multiply this first fraction by x to the 1/3, multiply by x to the 1/3, and that's going to leave us with 5x, because x to the 2/3 times x to the 1/3 is just x, plus 10 all over 3x to the 1/3. You could change the x to the 1/3 to the cubed root of x. So to find where the function's increasing and decreasing, we are going to need to make a sign pattern chart. but first we need our critical numbers. So we have our first derivative here. We're going to find the critical numbers. The critical numbers are found by finding where this, so I'll just write it here. We need to know, where does f prime of x equal 0, or where does f prime of x not exist? These are the two things we need to know. So f prime of x will equal 0 if the numerator equals 0, and that's going to happen when x is -2. And this will not exist when the denominator equals 0, which would be when x is 0. So these are our critical numbers. So I'm just going to, let's highlight critical numbers. So to find where the function is increasing and decreasing, I will make my number line, and I will put both of these numbers on here. And I want to know what's going on in each of the intervals. So I'm going to use a different color. So I want to know over here, is f prime of x going to be less than 0 or greater than 0? I'm writing it like this now because I think it's more clear instead of just writing a plus or a minus. Just because when you're dealing with the problem like this, where you're dealing with the first derivative and the second derivative, it's easy to lose track of your work. So in this one, we have f prime of x, and let's see, if we plug in something like -5 or -3, right? If you plug that into the function, you are going to end up getting a positive. You're going to get a negative over a negative, which is a positive. So here, the derivative is positive. In this region, the derivative is negative. And in this region, the derivative is positive. And this was done earlier. That's how I did it so fast. And so what does this tell us about our function f? Well, when the first derivative is positive, that means that f is increasing. Here, f is decreasing because the first derivative is negative, and here f is increasing. And this is what I was saying, since we've basically just done most of the first derivative test, we may as well just add in what the maximum and minimum are. So if we switch from increasing to decreasing on our function, that means that we have a local max. And if we switch from decreasing to increasing, we have a local min. Okay, cool. So that's the first part. And then we're also asked to find where it's concave up, concave down, and any points of inflection. And so to do that, we need the second derivative. So when you find the second derivative, I recommend just using this guy right here. Don't use that one that's a fraction below, because then you're going to have to use the quotient rule, which is more of a pain. So just, or I mean, you wouldn't have to use the quotient rule, but just keep it basic. Go from the start. So we're going to do this, and we will get 10 over, let's see, bring the 2/3, 10 over 9 x to the -1/3 plus, or actually will become a minus 10 over 9 x to the -4/3. And so I'm just going to rewrite this by moving those x's into the denominator. And if we want to make a common denominator here, we're going to need to multiply this first fraction by x over x. That's because x to the 1/3 times x is x to the 4/3, and we already have the 9 there. So this is going to become 10x minus 10 over 9x to the 4/3. So that's our second derivative. We found it. And so remember, to find the possible points of inflection, we want to use that guy. And these are just possible. I'm going to abbreviate points of inflection as POI. you want to find where the second derivative equals 0 or where the second derivative does not exist. So it's like finding the critical numbers for the first derivative, but now the second derivative. So I'm going to set my numerator equal to 0. 10x minus 10 equals 0 when x equals 1. Here, I'll write the whole thing. Means x equals 1, and then we would set the denominator equal to 0 because that's where that will not exist, and that would be 0. So the possible points of inflection, oh my god, highlighter. The possible points of inflection are 1 and 0. Okay, so we have a lot going on here. So now to actually find the points of inflection and to find the intervals of the concavity, we are going to make another sign pattern chart. Put on the 0, put on the 1, and now we are dealing with f double prime. So let's go back to the blue. So over here, f double prime of x is less than 0. In the middle, f double prime of x is less than 0. And greater than 1, we have f double prime of x is greater than 0. And so here, in this first region, negative infinity to 0, f is going to be concave down. In this next one, f is still going to be concave down. So notice it did not switch. It didn't switch concavity, and so 0 would not be a point of inflection. But for this last one, f becomes concave up, which tells us that 1 is a point of inflection. And that's because f switched concavity. So now for the final piece, let's just summarize everything to answer the questions. So where is the function increasing? So we're going to actually write the intervals. So that takes us all the way back to over here. F is increasing from negative infinity to negative 2, and then from 0 to positive infinity. And use that same first sign pattern chart for where f is decreasing. It is decreasing from negative 2 to 0. Where is the function concave up? We are concave up from 1 to infinity. So this is looking at our second sign pattern chart that we made. And where are we concave down? We are concave down from negative infinity to 0, and then 0 to 1. I'm keeping those two intervals separated. And the point of inflection is at x equals 1, and then we did find local min and local max. Oops, so let's just add those in. Local min was at x equals 0, and local max was at x equals negative 2, just since we found those as well. So that was a lot. These types of problems can be a little bit lengthy if you have to find all of these things, but this is really, really good practice, and it's kind of like built-in review, actually. And in the next lesson, if you're interested, what we're going to do is we're going to do this exact same work, just finding all of these pieces and using all of that information to try to sketch a graph. And so if you want to challenge yourself, you could try to sketch the graph of this one that we just did. But that's it, you guys. I will see you soon. I hope you're all having a wonderful day, and I look forward to seeing you. Bye.